knows a lot about the science stuff. Professor Dave explains.
Moving along in our survey of the periodic table, we arrive at group 15. This is the nitrogen group, but it is also known as the Pnictogens. Beyond nitrogen, this group includes phosphorus, arsenic, antimony, bismuth, and moscovium. These elements have electron configurations ending in ns2np3, and metallic character increases going down the group, as does atomic radius, while ionization energy decreases. This means that nitrogen and phosphorus are nonmetals, which we should be quite familiar with from organic chemistry and biochemistry, while arsenic and antimony are metalloids, and bismuth and moscovium are metals. In this group, we begin to see a wider variety of possible oxidation states, all depicted here in this table. Nitrogen and phosphorus are capable of gaining 3 electrons to become nitride and phosphide. But positive oxidation states are more likely for these elements, with +3 and +5 dominating, given they will tend to lose or contribute to covalent bonds either their 3p electrons or all 5 of their valence electrons. Where can we find these elements? Nitrogen is exceptionally abundant, most notably being the primary component of the atmosphere. Diatomic nitrogen represents 78% of the air that's all around us. Phosphorus can be found in ores containing phosphate, like apatite, more than half of which is located in Arab nations, but also China, Russia, Morocco, and the United States. Interestingly, phosphorus production may have already peaked, which means a phosphorus shortage could be possible by 2040, and even total depletion within 100 years. Arsenic is also found in a number of ores containing iron, nickel, or cobalt, as well as realgar, also known as ruby sulfur. More than half of these deposits are located in China, with others in Chile, Peru, and Morocco. Antimony is found in the ore stibnite, with most of this located in China, but also in South Africa, Bolivia, and Tajikistan. Bismuth can be found in the ores bismuthite and bismite, again located largely in China, but also Mexico and Peru. Moscovium is another synthetic element that was first formed in 2003. As we have come to expect from transactinide elements, this is exceptionally radioactive, with its most stable isotope, moscovium-289, possessing a half-life of just 220 milliseconds, decaying into nihonium-285 via alpha decay. Structurally speaking, nitrogen is the simplest of these elements. It will form a diatomic molecule, which is a gas at room temperature, and there are no other allotropes. Phosphorus, on the other hand, has 3 allotropes. It can form P2 gas, just like nitrogen, and this is quite flammable. It can also exist as P4, where each phosphorus is bound to all of the others to form a pyramid. This is a white solid that ignites spontaneously when exposed to air, and is a key component of certain incendiary weapons used in war. And it can exist as red, purple, or black phosphorus, which are different arrangements of P4 subunits. Arsenic also has 3 allotropes, yellow, gray, and black. The yellow is structurally analogous to white phosphorus with the same pyramid shape. Gray is metallic and the most stable, and therefore the most common. Black is amorphous, similar to red phosphorus. Meanwhile, antimony and bismuth are both simply low-melting metals. So what do these elements do? As we said, nitrogen can form nitrides, whether covalent or ionic. Most importantly, nitrogen is a component of ammonia, which is key to the production of other nitrogen compounds. Nitrogen reacts with hydrogen to form ammonia in the Haber process, which we will investigate in more depth later. Ammonia reacts with oxygen in the Ostwald process to form nitric oxide, and then this reacts further with oxygen and water to form nitric acid. Nitrogen can form hydrazine, or N2H4, which burns in air and is a powerful reducing agent. It can form a variety of oxides such as nitrous oxide, or laughing gas, nitric oxide, as we mentioned, nitrogen dioxide, nitrogen trioxide, dinitrogen trioxide, dinitrogen tetroxide, dinitrogen pentoxide, as well as the nitrate and nitrite anions. Phosphorus is quite interesting as it forms cage molecules with oxygen. Examples of these are P4O6 and P4O10, which have the following structures. It can form similar compounds with sulfur like P4S10 and P4S3, the latter of which is used in the heads of strike-anywhere matches. Both nitrogen and phosphorus also form halides, such as phosphorus pentachloride, which we discussed in organic chemistry. In terms of broader applications, nitrogen is crucial in the production of fertilizers, which are needed to feed the global population. Liquid nitrogen with a boiling point of negative 196 degrees Celsius is the cheapest and most available cryogen, which is a substance used for attaining low temperatures, something that is important for preserving biological samples. Nitrogen is much more inert than other atmospheric components, and thus offers a stabilizing atmosphere for fuels and explosives, air-sensitive laboratory chemistry, and cheap incandescent bulbs. Phosphorus is also needed for fertilizer production in the form of phosphates, and in fact, depletion of phosphates from soil has caused mass starvation throughout history. Other phosphorus-containing compounds are used in the production of baking powder, additives, flame retardants, pesticides, and detergents. We will also likely recall that phosphates act as the backbone of nucleic acids and are also essential for biochemical signaling, thus playing a fundamental role in biochemistry. Arsenic is most famous for its toxicity, whether in the form of arsine gas or poisonous oxides. This became known through its usage, such as with a pigment used in art and wallpaper in the 1800s, which gave off vapors that could sicken or kill those in the room. Arsenic still has some utility in gallium arsenide, which is a semiconductor. Surprisingly, there is evidence that arsenic is required in very low concentrations for optimal health in chickens, and is thus fed to chickens in the form of roxarsone. This may even be the case for optimal metabolic function in humans. Antimony can be added to lead to make it harder, which is often done to harden lead bullets. It is present in linotype alloys, also containing lead and tin. These alloys expand slightly when they solidify, which forces metal to fill molds, thus preserving sharp edges and features. This was applied by Johann Gutenberg in developing the printing press, which revolutionized human civilization. Bismuth is completely non-toxic and is best known for its presence in Pepto-Bismol, a diarrhea medication whose active ingredient is bismuth subsalicylate. It is also present in a component of scintillation detectors and alloys used for fire detection systems. And that completes our introduction to the pnictogens.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.